So I'm at ZF, which is a large sort of traditional tier 1 automotive supplier. I'm responsible for both safety and security, system safety and product security. But today I'm not really going to focus on security at all. I'm interested in both how do you scale up traditional system safety processes to autonomy and AI, and then also how do you use that to gain some measure of trust so that we can ultimately deploy these systems, which I think was the point of really the workshop the last couple of days. So at ZF TRW, we're all about basically safety products or safety critical products. So at any one time we might be running 300 different system safety programs at the same time. So it's a fairly big enterprise of activities where we're running safety programs on everything from electric power steering to airbags to to sort of modern active safety systems like lane keeping, adaptive cruise control, automatic emergency braking, and the like. So my talk is pretty simply organized. I'm going to talk a little bit about system safety. So part of my job, I think, also today is to stick up for traditional system safety and, again, explain how it might get scaled up. And then I'll talk a little bit about this issue of trust and system safety. And then finally, how we might do the scale up thing. All right, so this is maybe a little bit flipped, but ultimately my job, I tell people, is that is to stick up for what the product shouldn't do, right? So to me, this is what system safety is really about. And so I'll credit Ross Anderson with the quote of safety is programming Murphy's computer and security is programming Satan's computer. But that's really the idea, right, is to understand not only what could go wrong, or not only what shouldn't happen, but how did it go wrong to get there? So for instance, if I think about pedestrians in the crosswalk, in my world, that would be part of the functional requirements for the system. The system's supposed to detect pedestrians in the crosswalk, and in fact, I would expect that someone developing that system would expect anything that could reasonably be in that crosswalk, and including somebody in an electric power, chair or whatever, would be detected in the crosswalk. And so my job would be to determine what could go wrong with the system such that, if I've looked at everything that I should normally classify as being in that crosswalk, how did I miss this one thing, right? What would go wrong that would make me miss that thing? All right, so I'm going to go through a few definitions here, and this is a little bit dry, but bear with me. There's reasons for going through it. So system safety is ultimately about the absence of unreasonable risk. So this is a pretty important concept because, and you'll see this throughout this talk, it's really about a risk acceptance activity. So there's no such thing as perfect safety. Second thing is, and this was noted several times, a newly introduced product should not increase risk to the general public over what it was before you introduced it. So that's often something that you'll need to leverage to bash your way through these safety programs. And then finally, the way we normally think about it is it's resulting from a systematic effort to identify what the system should not do, design them to avoid unsafe behavior, analyze that this has been achieved, and document the evidence, which is something I constantly have to remind people. It's like if you don't write it down, it didn't exist to some extent. You don't have a safety case, which is the next thing. So the safety case is evidence that safety requirements are understood together with the evidence that the system complies with these requirements. And then ultimately you want to have an argument for why that's good enough, right? So what are you going to use this thing for? Well, I mean, if you're basically certifying airworthiness, then you have to have a certification. But in almost every other field of endeavor that system safety is used that I'm aware of, it's really a risk acceptance activity. So what happens is there's some chief engineer or somebody in some level of authority that's going to sign off on something going to production. They're going to take this safety case, in addition to other information that they get, in order to make a decision about whether they're going to accept the risk of deploying that thing or not. And I'll skip over hazards because I think we talked about that too. So the last couple of points are that system safety actually doesn't care about bugs, failures, mistakes, whatever, unless they lead to hazards. So safety is not equivalent to reliability or quality. And when you get to the actual design problem, though, of course, you got to bring everything back together. And I tend to think of it as sort of one giant optimization problem. So I throw all these things in together and I try to come up with something that isn't hugely expensive just to solve the safety problem. All right. So conceptually, in system safety, what we do is we identify the hazards, which we've talked about before, and then ideally we would avoid hazards, which is something that most people don't really think about, but turns out to be extremely important, I think, when we're going to start deploying autonomous driving, which is what I'm mainly interested in. Then we evaluate the residual safety risk and make the decision whether it's okay to go forward, and if not, we start adding stuff. Now, at each point in that feedback loop, the system that contains now elements to improve safety, we typically call that the safety concept, which is, I think, an important point going forward. So that's the architecture and all of the implementations of all the different features that we're using for safety. You can do the same thing with security, but I'm not going to spend time with that, I think. So now, in the evolution of system safety, the early system safety processes followed pretty closely that closed loop approach, right? I mean, that was fundamentally NIL Standard 882. That's what we used. It's completely general, but it doesn't really provide very much guidance, for how to do this work. So around 1980, attention turned to what we now call functional safety, which is really focusing on just the software and the electronics, because everyone decided that that's the part of the system whose behavior is potentially predictable, but really nonlinear. So if I have a software bug, a single software bug can have a huge impact on the overall safety of the program. So I better get that part right, or maybe it's a failure on a microprocessor. So the entire safety program was built around that, and we started to add some of these other features like systematic versus random failures. Systematic failures would be like software bugs versus random failures, which are hardware failures. Included controllability in the risk assessment, things like that. One key thing that we developed was integrity levels, which, once I've done this risk assessment, I quantize now the risk into various different levels, and at each different level, I have a number of derived requirements that are specifically implied by being at that level of required integrity. So this works across DO 178, IEC 61508. Those are the most influential, I think, so far. But then in 2011, we have one for automotive, which works pretty much the same way, called ISO 26262. And if you work in autonomy for vehicles, you've probably heard of that one. So if functional safety only focuses on the controller and the software, then we need to handle physical systems separately. And then also in that time frame, we had a number of other approaches to system safety, promoted by Nancy Levison and folks like her. So if I want to handle a system safety program, I got to do the functional safety. Then I need to have another approach for the safety of physical systems, which is similar but not exactly the same. And then now recently, we're worried about what's called the safety of the intended function, or SOTIF. So things like that. And now we're starting to get into the types of failures that you might be worried about in autonomous driving, but they're not quite exactly the same yet. So we're worried about things like, if I have automatic and emergency braking, if I brake with too high force, too many G's, then do I cause accidents behind me because now I'm stopping too quickly? So I've created hazards by implementing this safety feature. So so then I got to build fairly detailed requirements around that. So now the question becomes, is artificial intelligence and machine learning the next leg of the safety tree? But I can say for sure that in the autonomy world, we're going to tax all these areas. So the point of this slide is just to point out that now that I've unrolled the system safety loop and it's kind of a feed-forward approach, now I can align to the systems engineering V, and I think you might have heard Mike talk before about system safety in the V cycle. So we just have steps at each different phase of the process that we do for safety. We do hazard analysis up front, and then we flow those down to requirements, and then the functional requirements to become technical requirements, like how many faults I needed, what percentage of fault detection I need to have, and the like. And then I move my way back up a verification tree. Maybe one important point to make here is that I think the system safety community definitely welcomes all of the verification techniques that we've talked about today. But if we don't have those, we're going to bash through and try to verify things anyway. I mean, we have to get an answer and give the folks who are going to make the risk decision enough information to make some kind of a decision. All right, now I'm going to move a little bit to the issue of trust. So it turns out that there was a fair amount of study of this idea of system safety and trust in the early 2000s. So a simple definition would just be reliance on the integrity, strength, ability, surety of a person or thing. The key idea here is that you would have some kind of a willingness to depend on that thing, whatever it is. Precise definitions, though, are hard to come by, and that's why these papers in the early 2000s were starting to look at this. And one of the things that they discovered was that trust and distrust are separate constructs that can exist simultaneously. So I can simultaneously trust some aspects and distrust other aspects, and I'm kind of making a trade-off decision. And I guess, again, with respect to the deployment of autonomy, we want to fall down on the I trust enough that I'm going to go ahead, right? But an important point here is that the quality of the safety argument is not sufficient alone to achieve this trust, okay? Stakeholders have to have confidence in the specification that you are working against, you know, when you created this safety program. So in particular, Littlewood and Wright, you know, they've formally modeled this whole verification process. And one of the things that they came up with was, it kind of doesn't matter how many legs of my assurance case I create. I could have, you know, multiple levels of diversity and things like that. If I didn't trust that the specification that led to all that was correct in the first place, you know, again, it kind of doesn't really matter. So the sentiment that underlines this confidence issue can evolve and is also subject to regional variation. So we talked about that a lot in the last couple of days too. Things are different in Europe than they are here. Okay, so the next concept that I think is important for autonomy especially, and you know, and again, Mike covered this partly. So I think most people here are pretty familiar with the concept of black swans, and we usually think about the first couple of different items of the definition of a black swan, but the third one gets, I think, a little bit passed over. And this is the idea that after the first recorded instance of an event, it's rationalized by hindsight as though the relevant data were available but unaccounted for. Okay, so we should have known that, but we didn't know it, right? I mean, and usually it's expressed that there's some kind of a bias or something that leads to us, you know, ignoring that. I think the point, though, is with respect to these type of system safety issues, we really need to, whenever you find a black swan or you start to perceive that there might be something out there, you can really infer a whole class of hazards from that observation of a black swan. So the black swan is not just a pure outlier itself. If it's really true that there was bias that led to you never seeing that in the first place, you need to think about what's the larger region of things, you know, that are kind of like that, right? So, I mean, it's, you know, so again, thinking about the autonomous system coming into a construction zone and missing the fact that it's an orange barrel, or the pedestrian situation of missing the guy in the wheelchair in the crosswalk. You know, once I've recognized that that's a limitation of my system, I need to think about all possible ways that could have gone wrong, not just that one instance, of course. And I think for most people that's really obvious, but you know, it may be hard. You know, it may be actually a good, you know, opportunity for machine learning, which is, you know, part of Mike's thesis. So I would submit that the challenge in autonomy and AI system safety in general is this hunt for black swans. And I think that the way that this shakes out is that verification and validation should be conducted only on what's known or against requirements that are captured explicitly. So that hunt for black swans isn't part of the V&V loop. The V&V loop is to basically solve a system safety case, solve a safety case around what I know. But after that, I need to have this hunt going on in the background, you know, where I try to update my understanding. So I'm gonna skip through this pretty quickly. I was gonna follow a notion that Claire showed yesterday, which is to ask a couple of questions that I thought were outliers and weren't really the answer. So safety case for autonomy doesn't look like the sum of safety cases for the constituent parts, nor is it, I think, completely determined by AI and machine learning. Instead, I need to partition the system into parts in order to be able to solve it, right? So I've got here, if I say that unsafe autonomy behavior can basically be broken down into, did I compute the path right, or did I make an error in following the path? I mean, that's sort of the most general, you know, description of the safety problem that I need to solve. And then, you know, there's a million subproblems that get solved under that. But the point is, the whole right branch doesn't involve any machine learning whatsoever, and I better be able to solve that with my traditional techniques. And then there's some part of computing the path in the first place that does involve machine learning, and there I should be able to now apply techniques like, you know, was described by Amodi and all. So let me just move near the end here. So the safety concept for now autonomy, and I think this has been described quite a lot over the next couple of days. Almost every autonomy system that I've seen looks something like this. So there's complex logic on the right-hand side that's through your decision logic, and you might be able to break that down into various different partitions. Then you have some system safety monitor that checks and remediates that. And you might have actually many levels of that, because ultimately you want to get to something really simple that isn't subject to failures in machine learning or other things like that. But then the more important point here is that outside of that, I need a meta safety and availability system whose job it is to update based on things like black swans. So I'm never executing my safety process, like I say, on thinking that I'm going to be discovering black swans. I always add those in later. And that process requires potentially a complete system update. It may not just be learning. All right, so the last point that I wanted to make was some thoughts on our trajectory toward trust agreement. And again, these have been covered a lot of in the last couple of days. The first thing, if we need to have general agreement on requirements, we need to include all the stakeholders. The next thing is that we need more precise definitions for autonomy systems classes. And there's a NHTSA definition and there's an SAE definition of levels, but those don't really include the environmental bounds that would allow me to sort of bound this away, so that I don't have as many black swans inside that region at any one time. And then I think we need to agree on hazards that are known right now for each class and agree to update as we find these new things. And also agree on how we're going to do that. And then I think we need to agree on some of these verification techniques and start to use them. So I think that pretty much covers the key points. So, all right, thanks.